Blue Ringed Octopus and Cell Signaling. Introduction. Blue Ringed Octopus is a small and highly venomous cephalopod. Blue Ringed Octopus are known for being extremely toxic, and they secrete Tetrodotoxin, which ultimately results in death. And there's a picture of a Blue Ringed Octopus right there. Tetrodotoxin, here's a summary, is a deadly toxin attacking the axon of neurons found in the CNS or central nervous system. They do this by blocking voltage-gated sodium channels in the nerves. This prevents the formation of action potential within the nerve. Action potential is required to release neurotransmitters. Having no ion channel prevents the gathering of action potential, and having no neurotransmitters halts muscle usage, which will eventually stop breathing and ultimately kill people. Cell signaling pathway. So the ligand for voltage sodium ion channels is usually sodium or Na+. But in this case, TTX or tetrodotoxin acts as a ligand and blocks the channel, preventing sodium from getting in. The receptor in this case is the voltage-gated sodium channel that allows sodium ions into the axon of the nerve cell. The axon is the long part of the nerve cell, by the way. Basics of the pathway. So the NAV, or sodium voltage gate, allows Na plus into the axon. Positively charged ions pushes open the gate of the sodium ion channel, allowing more ions, causing a chain reaction down the axon. Action potential. Action potential increases as sodium ions flood into the axon. Action potential is kind of like the electrochemical gradient of the axon. So more positive things inside it would mean more action potential. And this overshoots the equilibrium of the electrochemical gradient, and this turns the axon from on the inside from negative to positive in like a wave-like pattern. This fires a signal down the axon. Cellular response. The cellular response of the sodium ion channel is the firing of the nerve, resulting in neurotransmitters coming out of the axon terminal or the end of the nerve. Typically, the axon is negative until the signal fires. This is because more positive sodium and potassium ions are on the outside of the cell. Then the gate opens and the flooding of ions changes the electrochemical gradient, letting the inside be positive. Action potential will then increase in a wave-like pattern throughout the axon. Once the signal reaches the end of the axon, neurotransmitters are sent out. Meanwhile, action potential then decreases from potassium ions in order below the starting point as the axon recharges for another signal. All right, I have a visual, or a few of them here. So starting with the top left, I have a picture of an axon. So that membrane right there is the axon, and on the bottom is the inside of the axon, and the signal that's fired will actually go the way of the blue arrow on the bottom. But for the sake of teaching, I have to start with the channel on the right. So the channel on the right is closed, and that channel is in its relaxed state. Now, if we look at the sodium ions flooding in from the left going to the right, those are positively charged, and they will push the two positively charged pink columns up, opening the gate. And then if you notice how the sodium channel in the gate is opened in the middle, that is from the positively charged sodium ions will push the positively charged gate up and open the gate in total. The middle gate is allowing more ions in, and then the ions will disseminate into the right or like down the axon to create the positive like wave down the axon. And then the leftmost gate is closed by a different stopping mechanism that is like unaffected by the sodium pushing up on the pink opening gate, and this prevents like too much buildup of sodium. Okay, now if we look on the graph on the right, it's a map of the action potential in the axon in the process that we just have on the top picture. So highlighted is the resting phase. This is like the baseline, and the axon in this graph, the resting phase is negative 70 millivolts, or a negative charge. And then it goes to the depolarization phase, going up to negative 55 millivolts. This is like the starting of the signal. And then this will cause the voltage gated sodium channels to open, going from the top picture, like left to right. And then this will push like it will overshoot the equilibrium, so it will eventually go up to positive 30. Now the inside of the axon is more positive than the outside. And then sodium channels close so the ball shaped stops will close on it, and then potassium channels that aren't shown here will open, and K plus ions will flow out. So that's shown by like the decreasing part of the graph. This is a repolarization phase. And then the next one is the hyperpolarization, which is shown by going below the resting potential. This is like the combination of potassium ions flowing out and the ball stop being there. And this allows the axon, like this doesn't allow the axon to fire again too early, which is like pretty important. All right, here's the faulty mechanism. And so this diagram comes from like an interesting article discussing TTX and its potential for pain relief therapy. So I zoomed in on the diagram and then on the right we have the zoomed in version under the pink arrow, and it shows how TTX just physically blocks the sodium voltage ion channels. And then this ultimately prevents the transmission of the electrical signals, and then prevents neurotransmitters. But mostly for TTX, this like just prevents muscle movement, breathing, whatever. Okay, in summary, Tetrodotoxin from Blue Ringed Octopus block voltage-gated sodium ion channels in the central nervous system neurons. This prevents the buildup of action potential and stunts neurotransmitters, resulting in the failure to move muscles and breathe. Here are my sources. Sorry for going a little over time. And then here's the second page of sources. A lot of the photos came from YouTube videos, so I had to put those in the sources as well.